Lesson 14, we're going to look at compositions of transformation. So basically what this means is we're going to apply multiple transformations on the previous function that we come up with. So you think about composition of functions, you take the output and then you plug it back in to the function or into another function or the same function to get another output. Compositions of transformations is going to be the same idea. We're going to just kind of pile these up and perform them one right after another. So basically for this first example here, we're starting with this quadratic function. So x squared is our parent function. And we have some different transformations that have been done to it. First one here is it's been translated 3 units to the right. So I'm going to call that number 1. And basically what I'm going to do is instead of having my function f of x, I'm going to call it g of x. And if I'm translating 3 units to the right, remember HIVO, to the right is horizontal, so horizontal is going to go on the inside, and horizontal you always do the opposite. So if we're going to the right, it's going to be in the inside of the function, so it's an x squared or quantity squared in this case, and we're going to actually end up subtracting 3 because we always do the opposite for horizontal movements. So that's the first part. Then we look at the next part here. It says a vertical stretch by a factor of 4. So this is going to be our second transformation. And we're going to use what we just got out to apply this second transformation. So vertical stretch means it's going to be on the outside. So let me call this new piece here h of x. So vertical stretch, we multiply by 4 because we do what makes sense. So if it's a vertical stretch, we actually multiply by 4. And it just goes on the outside, and we keep the other function just how we had it. So h of x represents the composition from taking x squared and translating it 3 units to the right, and then a vertical stretch by a scale factor of 4. And then the last one here is saying that after 1 and 2, we move 2 units up. So for this one, I'll call it k of x. I'm going to be taking what I just got out and now moving that entire thing 2 units up. So up is vertical outside, and you do what you think for vertical. So it would be +2, makes sense to go up. And this would be my new function. So I took the parent function, I did these 3 things, and this would be the equation of this new graph, or of this new function. So let's look at basically going the opposite way. So this example here says name the transformations that yield the graph of 2 times f of x plus 1 minus 3 from this parent function. So it's asking us what happened here. So if it doesn't specify an order to go, like it doesn't say, oh, go -3 first, or, so 3 units down first. If it doesn't specify, you just read this left to right. So basically, when I look at this, the first thing I need to worry about is that 2. So since I have a 2 out in front, that means it's going to be a vertical stretch because we're multiplying by a factor of 2. And then I look at the next thing. Well, the next thing that's different compared to f of x is this +1, x plus 1 in the inside. So since that's in the inside, again, remember HIVO, it has to be horizontal because it's in the inside, and you do opposite of what you think. So that means you would be going left 1 unit. So I'm going to write shift left 1 unit. And then the last part here is this -3. So since there's a -3 at the end, that's the vertical movement because it's on the outside, and we're going to go down 3. So translate or shift down 3 units. And that's it. So you would just go left to right in this order, and that would be the graphical representation of what this formula is saying to do. And one last example is now what happens if we're given equations like this, and now we actually have to go through and do the graph. So basically, we're kind of applying what we just did in the first two problems there. One where you had to come up with the equation, and one where you were given the equation or you were given the function rule and you had to pick that apart and understand what did it actually mean. So now we're actually given a equation and we need to basically pick it apart and figure out what are the individual pieces here. So I'm going to work left to right, and when I look at this left to right, I have a negative out in front, so that's going to tell me that I'm going to be reflecting. And since it's on the outside, that means it's going to be a vertical flip. So that means it's a reflection over the x-axis. So remember, anything on the outside, you're doing vertically. So it's negative on the outside. That tells me I'm flipping vertically. Then I look at the 3. Well, the 3 tells me it's going to be a vertical stretch by 3. Then I go to the next piece, this plus 5. So that's going to tell me, since it's in the inside, it's going to be a horizontal shift and it's going to be left 5 units. And then this plus 1 at the end is going to be a vertical movement and it's going to be up 1 because we do what makes sense. So basically what I'm going to do is I'm going to start with this parent function and I'm going to do each of these things to it. Now you could do them all in one step. I would recommend breaking it down into at least 2 different steps. Usually what I do is in my first graph, I'll do the reflection and the vertical stretch at the same time. And then once I get that, then I shift it. So then I'll do this part. So let's actually look at that. So we have our parent functions already graphed. One thing I want to point out with this parent function are some key points. We have 0, 0, we have 1, 1, negative 1, 1. So if you notice, for a standard form or a parabola, the parent function of a parabola or a quadratic, you're always going to have this 0, 0. And then to get to the next set of points, it's going to be over 1, up 1. Left 1, up 1. But then to get to the next set of points, when you go over 2 from the vertex, you're always going to go up 4 units no matter where it's located, because when you square 2, you get 4. So same here, I go left 2, I'm going up 4. So that's always the relationships, because it's always however far you go away, if you square that number, that's how far you need to go up. It doesn't really matter the actual numbers, it just matters that pattern. So for example, if I went 3 units to the right of the vertex, I square 3, I get 9, so it tells me I'd have to count up 9 units. Same with 3 units to the left, square that, you get 9, that means you're going 9 units up from the vertex. So basically, here's my parent function. What I need to do is I need to reflect this over the x-axis as well as do a vertical stretch. So one thing I want to make a note of here is whenever we do a vertical stretch, remember that that really means multiply the y values by whatever that factor is. So you're only multiplying the y values. So multiply y values by the factor. So what's going to happen is I'm going to flip this. So I'm going to take each point and I'm going to move it over the x-axis. So if I'm starting with this point here and I reflect it, it's going to just stay right on the x-axis. Because if you have a point on the line of reflection, it's going to stay there. But then when I go to do these points here, well, if you go 1 unit to the right of the vertex, you square 1, you get 1. But if you remember, we're doing a vertical stretch. So that means instead of me going right 1 and then moving 1 unit up or down, I need to do 3 times that because this has a vertical stretch of 3. So I'm actually going to go over 1 and then down 3. So these are basically, this point I just plotted came from this point right here. So same with this side. Instead of just plotting -1, -1, it's actually going to be -1, -3 because I multiplied the y value by 3. When I get to this point here, so 2, 4, it's actually going to become 2, -12 because I'm multiplying this 4 by 3. So I'm basically tripling the distance you go from the original. So here I'm saying, okay, if I square 2, I get 4, but I have to triple that 4. So that's not going to actually fit on the graph. So I'm going to leave it as these are my 3 key points. And I'm drawing this one dotted because this is kind of the in-between step. This isn't the actual final graph. And then if you look, so this is the in-between step. I did the reflection over the x-axis and the vertical stretch by 3. To finish it up, I need to move left 5 up 1. So I'm going to do all of that together. So I'm going to take each of the key points that I just plotted, move them left 5 up 1. So 1, 2, 3, 4, 5 up 1 is my new vertex. 1, 2, 3, 4, 5 up 1. 1, 2, 3, 4, 5 up 1. And this is going to be my actual graph of this equation. H of x equals -3 times the quantity x plus 5 squared plus 1. So this is going to be h of x. So that's done. So now the next one we're going to do, first thing we're going to do is we're going to decide what are we doing to this. So we have a 2 out in front that tells me it's going to be a vertical stretch by 2. No reflection this time because I don't have any negatives. Then I look here and I have a plus 4, so that means I'm going to be going left 4 because it's in the inside. And the -3 tells me down 3 because it's on the outside, so we do vertical. We follow what makes sense, so negative means go down. So again, I'm going to break this up into 2 parts. First thing I'm going to do is the vertical stretch. So I always do the stretches and the reflections together. And then once I get that graph, then I'm going to shift it. Then I'm going to do the left 4 down 3. So a vertical stretch by 2 means I'm going to look at this parent function and I'm going to take each of these coordinates and multiply the y values by 2. So for example, when I start with this parent function at the vertex, 0, 0 is just going to stay 0, 0. But when I take this coordinate, which is the coordinate 1, 1, I multiply the y value by 2, my new coordinate is going to be 1, 2. Basically, think about it as you're doubling the y value distance. So here I went from the vertex over 1 up 1 to get to the original. I need to double that vertical distance. So over 1 up 2. Over 1 up 2. So here I went over 2 up 4. To get to the new point, it would be over 2 up 8. You're doubling the vertical distance. Over 2 up 8. So you could, if you wanted to, plot those in here. But it goes off the graph. So I'm going to draw this one dotted. Because that's the in-between graph. And again, it should look like it's actually stretching. So if I'm stretching vertically, you're pulling this up, which means it's getting skinnier. So it should be skinnier than this other one. Same with this one that had a vertical stretch by 3. That should be even skinnier than this blue one because you're stretching it even more. So now that I have my vertical stretch done, now I can take those key points I plotted and move left 4 down 3. So I'm just going to do these 3 down here. So left 4, so 1, 2, 3, 4, down 1, 2, 3. 1, 2, 3, 4, down 1, 1, 2, 3. And then 1, 2, 3, 4, down 1, 2, 3. And if you want, you could translate these as well. So 1, 2, 3, 4, down 1, 2, 3, and 1, 2, 3, 4, down 1, 2, 3. And then you can connect your graph. And this is going to be the function k of x. So that's it. So basically you've seen all the different pieces. You've seen taking an equation and breaking it apart and understanding what it means. You've seen given function notation using compositions, breaking that down and seeing what it means. You've seen how to break an equation down and graph it. You've also seen given the description, so like that first example, you were given the written description and you had to come up with the equation. So you've seen all the different ways that we can do compositions with transformations.